Here we go. Somebody did want me to do the benzaldehyde question, so I'll do that. Even though some of you might have seen it, let's just kind of clarify how that was supposed to be done. We have this as a critical point at temperature pressure here. 422 degrees C. It has a pressure of 45.9 atmospheres. And then it has a normal boiling point at 179 degrees C. So that must be 1 atmosphere. And then you want to know the vapor pressure, P, at 91.5 degrees C. Okay? So you want to know this one. The problem in this question with benzaldehyde is you don't know delta H. It's not given. They want you to find it. So here's the strategy. What you were supposed to do is say, take these two, use Clausius-Clapeyron to find delta H of vaporization. Once you have that, then we're going to pick your favorite one of these two and solve for pressure here. So let me write that out so you can see how it works. First, I'm going to find delta H of vaporization. Natural log of, I'll just call this point 1 and this one point 2. Okay? Natural log of P2, 1 over P1, 45.9, equals delta H of vaporization, I don't know that number, divided by R, 8.3145. 1 over T1, 422 plus 273, minus 1 over T2, 179 plus 273. So you can see here the only unknown is delta H of vaporization. Is that okay? So you solve for that numerically. Then, which one's your favorite? The first one or the second one? Oh, a lot of people like the second one. We'll take that one. Okay. Now, just to not confuse the numbers, I'm going to scratch that 1 out, and I'll just call this one 1. Okay? It didn't matter if we picked the first or the second there, but I just want to pick 1. So now that you have delta H of vaporization, you're going to say, well, same thing. Natural log of P2 is 1 over P1 is the P, equals delta H of vaporization, I just found that number from the previous calculation, divided by 8.3145. 1 over T1, that's 91.5 plus 273, minus 1 over T2, 179 plus 273. Now here, the only unknown will be P. Solve for that, and that's the pressure at 91.5 degrees. Is that okay? You just want to double check. Make sure you can do these calculations with your calculator. Again, that's a really common mistake here. All right. Somebody up here had a question. Yes? You're first. Yes, Therese.
Can you do on spring 2012, number 14?
Okay.
It's kind of like the Molality one.
Okay. Let's see. Let me see if I brought that. Can't remember. Spring 2012. Number 14. Is that? I think that's what it says. I lost it. Yeah. And this is the one about the ethanol water solution?
Yes.
Okay. Here you go. If you have any sleuth detective ability within you, you'll notice every single year I have a question like this. So it's probably a good one to know how to do. They can vary in the way they're worded, though, and then what concentration I ask for. But in this case, we have ethanol, ethanol water mixture. It's prepared by dissolving 20 milliliters of ethanol. I'll just say E. And I have the density is 0.789 grams per milliliter. And sufficient volume to produce 50 milliliters of solution. And the solution has a density, so this is density of the solution, not ethanol. This one's of ethanol. Density of solution now, after it's mixed up, is 0.990 grams per milliliter. For this solution, calculate each of the following. Okay, 3 sig figs, etc. Okay, so just to make sure you got this, we have here ethanol, and there's 20 of it, so I must have added about 30 of the water to get up to 50, right? Yeah, to produce 50 milliliters of a certain density of solution. So I'm just adding water, because it's ethanol water solution, to make the total. Is that okay? All right. So I want things like molarity, molality, mole fraction, volume percent. To do that, I will need like the mass, I'll need the moles, depending on what they're asking me, I might also need volume of ethanol, E, and I'll just put W, water. So I need the mass, moles, and volume of both of those, really. Okay, so what I'm going to do, the way I usually do these problems, I find all this stuff first, and then I calculate each concentration after I have my base set of variables. So you could do it one at a time. I just think it's a little faster if I have all of them separately. Okay, so what I'm going to do is find all of those, and then I'll actually get to the question. So, for example, ethanol mass of ethanol would be 20 milliliters times its density, 0.789 grams per milliliter. This will get me the grams of ethanol. Is that okay? All right, I can do let's see, what else could I do? The density, oh, that's the grams. I could find the moles. I'll use N, like in chapter 6 of 2A, N for moles. Moles of ethanol would be, let's see, it's the mass of ethanol from the previous part of the problem, times the inverse of the molar mass, and ethanol is given in the problem, it's C2H5OH. So from the periodic table, I can get the moles of ethanol. Is that okay? Okay. So I'm getting there. I'm getting mass and moles of ethanol. So that's a good start. Let's see, what else should I find? The water. Let's get a different color for water here. My purple pen go. Oh, here it is. For water, we have 50 minus 20, or 30 milliliters of the water. Is that okay? Because that seems like I had to add 30 to get up to 50. So 30, oops. So now let's find the mass of water. Oh, not ethanol. Mass of water. Well, that's 30 milliliters. And I know the density of water. If you forgot, it's going to be on the back of the exam. Is that okay? So this will be the grams of water. And I know the moles of water. Oh, that's a lot of W action going on. So that's W. Okay, so that's the grams of water. And I happen to know the molar mass of water. It's 18.02 grams per mole. So this is going to give me the moles of water. Is that kind of okay?
Yeah.
So now, let's review mass and moles of ethanol, mass and moles of water. I think I'm pretty good. I think I can do the problem. If I'm missing something, I'll just go back and calculate it. So let me try to actually solve the problem and see if I can get anywhere. Yeah?
So you wrote V up there, but you don't need to find it?
What's that?
You wrote V on there, but you don't need to.
Oh, yeah, thank you. Did I miss that one? I'll put that at the very bottom of the page here. The volume of ethanol is 20, because that's how much I started with. And then the volume total was 50. That's how much I ended with, I believe. Is that right? Yeah, 50. And then, so the volume of water must be 30. Is that okay? I think I got everything I needed. All right, now let's try the problem. Okay, so in the problem, molarity is the moles of solute, that's ethanol, over the liters of solution, that's everything. The moles of ethanol was up there. I didn't calculate it. Moles of ethanol. The liters, how many liters of solution? Yeah, it's 50 milliliters, or in liters, 0.050 liters. Okay? For molality, that's the moles of ethanol over the kilograms of water. Moles of ethanol we found up above. Sharice, is it okay if I do it like this? You'll find the moles of ethanol later?
Sure.
Okay. And then kilograms of water, I found the grams of water up here. See grams? So I'm just going to change gram. I'm writing the same thing again. But I found the grams of water, I just changed it to kilograms. Is that okay? Okay, what else did we have? Mole fraction. The mole fraction of ethanol is going to be, is that what this one? Yeah, mole fraction of ethanol is the moles of ethanol, so you need to know all these definitions. Divided by the total moles. Or, just to write it out more explicitly, the moles of ethanol divided by the moles of ethanol plus the moles of water. We actually found all these variables already. So again, you would just plug this in. So then, that's why I find all the variables first, and then I can just plug them into the formula, assuming you know the formula. And then the volume fraction, or the volume percent, is the volume of ethanol divided by the volume of total. Well, this one's pretty easy. The volume of ethanol, we already had that. That was 20. Divided by 50 for the total, and just times by 100%. Yes? You don't have to change the volume to liters. So don't worry about the units for volume percent or mass percent. But it is important in all the rest, pretty much everything else. It's important. One more thing. This is a problem here. I think, yeah, 12. How did I do that? 2, 4, 6, 8. Oh, so this was, I guess, 3 points each. So that would have meant 1 point for the correct units and 2 points for the correct answer. I told you in the problem 3 sig figs. If you didn't do 3 sig figs, we would have knocked you off at least a point for the whole problem. And 2 points for the correct answer for each. And that means 1 point for writing an M here. 1 point for writing a lowercase m here. 1 point for writing nothing here, because there's no units for mole fraction. 1 point for writing a percent sign here. Does that make sense how that's graded?
Yeah.
Okay. It depends if it's a 3 or a 2 pointer per, but if it's a 2 pointer, it's 1 point units, 1 point numerical answer. Okay?
Thank you.
Yeah. Just so you know how I grade. Yes, write units. If I tell you include units in your answer, we're probably grading you on it. Okay, who is next? Yeah. Leanna or something? Yeah, Leanna. Uh-huh. Yeah. Okay, so I'm wrong, which is fine. I'm happy with that. I have no idea. That's given. She's looking at page 21 in the reader, the second example at the bottom of page 21. Did you get a different math answer? Oh, did I use the wrong one? I don't know. Yeah, it could be wrong. I don't know. Nobody said anything yet, but if you think, yeah, let me know in lecture. Yeah. Yeah. Oh, it could be, that could be the wrong answer. The pressure might not be 1.4. Yeah, I believe you. Sounds good to me. Okay, who's next? Yes?
2004 liberation.
Yeah, just take a look here. Oh, okay. Do you, just solving the problem, how to solve it? Okay. Is it okay if I just steal your whole book? Because I forgot one. Okay. Here's a problem right here. Multiple choice in this case. Let me just do this. And then I'll just write on top of your book. Okay, test lab problem. Here's the overall reaction. CH4 is something, I don't want to start with CH4, it appears too much. O2 is a good one to start with because it only appears twice. So let's start with O2. I need a half, and so I'm going to take this here and multiply by what? Anybody?
1/4.
Yeah, 1/4. 2 divided by 1/4, that'll be a half. So I'm going to multiply this by 1/4. And that was to match up the O2. So I'll underline that, I guess. O2, O2. Matching up the O2, I need a half, so I divide by 4. Okay. CO, not helpful, it appears too many times. H2 appears too many times also. So that's all I'm going to get from looking at the overall reaction. My next step is look for intermediates. What would be a good intermediate to choose right now? H2O would definitely be fantastic because I've got one there and one here. Only appears twice. That's always my preference. It'll make your math easier. So let's get a different color. I'm just going to deal with underlines here because it's so small. So I have 1/2 here. So what do I need to multiply this by? Yeah, 1/2. That'll give a half in the products, a half in the reactants. They'll cancel. So I'm going to multiply this by a half. Okay. Now, what is the next intermediate I should take a look at? I have two choices actually. Oh, no, one choice. CO2 is the best one because it only appears twice. CO2 must cancel. I have 1/4 right now from reaction 1 in the products. So I need what? I hear the yawns of joy. Okay. No, I totally lost it. Oh no, 1/4. So I need 1/4 here, right? Okay, so I'm going to multiply the second one by 1/4. Add these three numbers, and that'll be your final answer. Is that okay? Cool. Okay, I'll keep you here for a second if people are still writing. Next question. Okay, a couple more, yeah.
Are you going to do like X-ray diffraction by problem?
What did I do?
Because on the homework there was an X-ray diffraction problem.
There was an X-ray diffraction. Oh, yeah.
Is that going to be on?
No, I think, yeah, I accidentally skipped it in lecture, and I didn't mean to, so I can't put it on the exam. Yeah. I think I just turned like 2 pages at once, and I was like, oh, go to the next topic. So yeah, I can't have that on the exam. Okay, who's next? Yeah.
A beaker containing a solution of sugar and water is coupled with a watt glass and then heated.
Yeah, sounds good.
Drops are observed on the underside of the watt glass. This liquid is,
Genius. What is it?
I have no idea.
Oh. Okay. I love that question. Okay, let's see. I need to find blank here. Okay, this is a common type of question for me. You'll see it in a lot of different variations in the multiple choice. So we have, here's a watch glass. This is water's here and sugar, you said?
Yeah.
Okay, this is being heated. So that means this is vaporizing, okay? And little drops are showing up right here on the top, on the bottom side of the watch glass, but top of the system. Okay, anybody, what the heck is that drop there? I think there's only 3 choices. It's water, it's sugar, or it's sugar water, right? It's water, why do you think that? I agree. That's right. You're going to be able to boil water. Sugar doesn't boil. It's a solid. So when you're boiling sugar water, salt water, blah, blah, blah water, only water is coming off. Does that make sense? Because the solute is a solid actually when you take it out of solution. And so you're not going to have a solid floating up to the top. And so this is actually an easy way to separate a solute from a solvent, and it would just be water, and that's it. Now, if this was 2 liquids, for example, water and alcohol, then on the top you would have water and alcohol, okay? Depending on how hot it got. All right, good. Who's next? A common multiple choice question, by the way. Yeah?
Can you do the mercury problem?
Maybe. Let's see. Okay. Thanks for the laptop. You fools should be giving me laptops. Okay. Oh my goodness. Okay, let me see how much time we have. Oh, painful. This is the mercury question. Let me at least kind of set it up for you. And I want to refer you to my video. So maybe I can get a couple other questions done. But basically, you have mercury starting at negative 38 in this problem. Remember, the numbers could be randomized. And this is mercury. And it's going to, no, it's going the other way. That's the final, no, that's nothing. Okay, that's not even a number. Okay, it's negative 48, I think. Going to 25. There we go. This says it's mercury solid. This is mercury liquid. So that means you're going to go through a phase change. Meaning you're going to melt. Okay? So when you want to find Q total, how much total heat do I need to heat this up, melt it, and then warm it to the final temperature? You have 3 Qs. Q1, Q2, and Q3. This is to warm the solid. This one is to warm the liquid, and this is to melt. So the melting point is actually at minus 38.87. That's what I wrongly wrote first. Okay, so what I'm going to do, I'm going to warm the solid up to negative 38.87. Okay, that'll be Q1. Then I'm going to melt it, and then I'm going to warm the new liquid from negative 38.87 all the way up to 25. Does that kind of make sense? That's why there's 3 parts. There's a part for every temperature change, and a part for every phase change. Okay. So let's get a different color here. This one and this one, the Q will be this formula, mCp delta T, because it's a temperature change for those two. Meaning the mass should be the same, it doesn't change. In here, the mass is 11 grams. So the mass for both of these will be the same. Cp is different. And I think this might be one of the hard parts about it. Let's see. Specific heat of the solid and the liquid are both given. Okay? So this has its own Cp in the question. This has its own Cp in the question. And then delta T for number 1 would be final minus initial, or negative 38.87 minus 48. For this one, you're going from 25, or 25 is the final, minus negative 38.87. Is that okay? So you're going to use this formula for 1 and 3. For number 2, it's going to be a little bit different. Let me use a different color pen for that one. For this one, I'll do it over here. It's going to be, let's see if they give you delta H. Yeah, it's going to be N delta H. And whenever there's a phase change, a reaction, or a solution mixing, that's an enthalpy change. They give you delta H, and it's in kilojoules per mole in the question. It's 2.33. You need to convert your 11 grams of mercury to moles, and multiply to get rid of this unit, and then change it to joules. Is that kind of okay? I know it's sort of fast, but I just want to make sure I can get a couple more questions. You need this back? Just mess around too. Yeah, feel free. If anybody wants to give me laptops, that's fine. Okay, who's next? Let's do a couple more, then we'll finish. Yes?
U15 on strength of the test.
Can you pass it to me? I forgot my book. So, number 15. This is the Henry's Law constant problem. I'll try to do this one fairly quickly as well. Okay, it's this one right here. It's page 25. We want to do this for nitrogen, right? And so Henry's Law is for a gas and a liquid. And so nitrogen and water. So you need the constant for nitrogen, which is right here. They give you the constant for oxygen, but you don't need that because they ask you only about nitrogen. So you're going to use this 8.2 number, not the 1.62. Okay? And the formula would be, what's this one? C, the concentration, is Kp. The number they give you here, this is K. Okay, those are the Ks. So then you just need to multiply by the pressure. And since we're at 760 millimeters of mercury, the pressure, and 80% of it is nitrogen, I just say 80% of 760. That's the pressure, because it's like a partial pressure. So 80% of 760 times that K. Done.
When you use the C1 over P1 equals C2 over P2.
You would use, you'll see in the reader, there's like a C1 over P1, kind of looks like a gas law problem. That's only if your focus, if there's a change. So you're changing pressures and thus you're changing concentration, just like the gas laws. But here it's just constant, there's no change. So the C1, C2 doesn't mean two components, it means a change. Is that okay?
Yeah.
Okay, maybe one last question. I think, was there somebody up here who had a question? Oh, okay, over there. I was delusional.
Two pretty quick ones. There's like 1 gram of tritium in a lake that's like 10 to the 8 liters.
Okay.
1 in parts per trillion.
Yeah, sounds great.
So I was kind of confused on how to do that because parts per trillion is 10 to the 12. Like 1 gram of solute.
That sounds right, yeah.
Yeah.
So, how many tritiums are there?
There's 1 gram in a lake containing 10 to the 8 liters.
1 gram of tritium, that's this, for 10 to the 8th liters of water, I guess.
Yes.
Okay, and you want in parts per trillion?
Yeah.
So that's 1 gram per, well, trillion. I guess that's 10 to the 12, yeah. 12 grams is what we mean. And this would be tritium, and this would be water. Or the whole solution, but there's so little tritium, you're not going to add tritium to your solution. Okay, so I need this number in grams. So 10 to the 8th liters. Change this to milliliters. You'll see why in a second. 1 liter is 10 cube milliliters. It's because I know the density of water. It's 1 gram per milliliter. So now we're at 10 to the 11, right? Grams of water. So now, what you do, this is how I do these kind of problems. I would say, well, there's 1 gram of tritium given, divided by the amount of water given. Oh wait, 11? Eee, how do I change that? Okay, there. And then, I would go, I'm going to multiply by 1. So it's 10 to the 12, it's this number, whatever it is, 9, 6, whatever, over 10 to the 12, because I'm multiplying by 1. Okay. And this would be grams of the tritium, divided by grams of the water, essentially. Okay, this, let's get it black here. That is parts per trillion. So you multiply this times this divided by that, which would look like it would be 10.
Yeah.
Okay, does that kind of make sense? So I end up, all I need to do is find the grams of both, divide them like this, make a fraction, multiply by 1, depending on which one you're asked for. This is 12 and 12. If it was billion, it'd be 9 and 9, etc. And then know that that part, that this 10 to the 12 is going to become the parts per trillion. You're not going to multiply it in. Okay? Cool. Good question. Good questions, everybody. I will see you on Tuesday. And I think that's it. And I think I stole somebody's thing here. Did I?